Today we're going to learn how to code for a linear regression model. Basically, the purpose of this tutorial is to know how we can plot these two plots, y versus x, and the cost function versus iterations, and also to show how these plots or the relationships dynamically changes to get this final form. And for that, we'll need all these three equations. Uh, so let's jump right into the coding. So so we want to plot x y versus x. We also want to plot y, the predicted value y hat versus x. So these two plots, and for that we'll have to do something. So for plotting anything, we'll have to import a library that is called matplotlib.plt as plot file as plt. So here, matplotlib.pyplot is a module, and we have to call this module to plot any curve. Yeah. So it's still showing error because we don't have not defined x and y hat yet. So let's define x. So for any numerical computation or numbers and stuff that we normally use in coding, we'll have to import another library, which is called numpy as np. So here x equal to m, where m say is equal to 51. So we have defined x. X is we have called this function np.linspace. So this is creating m number of data starting from 0 to 1. In between these two values, it's gonna create m number of data and like equally spaced data. So and like within we define y, the real value is y x plus 5, say for example like this. For now, let's just disregard this. And now if we plot this, so this is the real data, and we have this straight line. So let's just change like how we want to see the data is. Say we want to see the data as this form, and then we can see that this is a straight line and the data are really nicely distributed because this follows this function. But in real, what happens when we get some data, or we basically measure them, or we get them for, using some sort of medium, and there is always some like errors associated with that, and that's why there is some noise. And so we'll have to add a noise for that, and the uh, noise. So the noise is dot random dot normal 0. So, so here we can see, like when we added this noise, which is defined by this equation, our data is more spreaded and it's more random. But one interesting thing is, say if we didn't have the noise, every time we run this program, we will have a consistent value of x versus y. For example, I should have shown that before, but let's see it here right now. So say I run it first, like there is no noise at the beginning. So first run it looks like this. When I run it again, it again looks like this, like there is no change. But when there is a when there is a noise that we are adding, so this noise we have added, every time we run, the data is going to be different. It's going to be different. Why? Because how we call this noise actually changes where for every run. So we're using our so here we can let's see from left to right. So this portion is a submodule under the module numpy, and from there we have this function. So this function basically calls a data set that is from a Gaussian distribution or a normal distribution, and this picks really randomly. So every time it picks, like every time we run, it picks randomly, and that's why it's different for each run. And what it only follows is the mean value, which is given by the first term. So the mean value here is 0, and the second term is standard deviation, which is 0.4, and the size of the data is actually the same as the size of x. So for every x value, there will be a corresponding noise that will be added to the value of the output value y. So yeah, so that is what we have we have plotted, and then we also want to plot the linear fit that that predicts this data set. So that is given by this, and here it shows error because we haven't defined yh. So yh is like we'll have to define, and from the previous lecture we know that yh is equal to y1 w1 multiplied by x plus w naught. So W1 and W, these are the weights that will have to provide the initial guess as well. So W naught is equal to np dot random dot rand. So this is another function. So under this submodule we have another rand function, and when we put here 1, it means that it's gonna randomly pick one value from for w naught, which is gonna be between 0 and 1. So but 1 is not included, so 1 something that is less than 1, but from 0 to less than 1, something like that. So we can actually see that print w naught w1. So if we run that, we will see that there is a line. So this line is representing the linear fit, or our predicted value, or the hypothesis function, which is the plot of for this line. And we can also see these values. These values are this value is the value of w naught and w1. As I said, that we are basically predicting, and this is gonna randomly pick any value from 0 to 1. And here we can see that this is from 0 to 0 to 1, but it's not gonna include 1, so it's gonna be 0 to 0.9999999, like any value between these two limits. And again, like every time we can see this value is gonna be changed because this is randomly picked. The guess is randomly picked. So this is really important to understand. And we can also provide the values ourselves. Okay, so another thing we can also change, we can change how the plot looks. Say we want it to look red. Yeah, so it looks red right now. But right now there the main portion comes that we want what we want actually. We want this linear fit to be better, because right now our prediction shown by this straight line is way off than the original data, um, uh, which is given by these cross marks, and this the gap needs to be reduced, and this gap is defined by the cost function, as we learned in the previous lecture. So what we want to do, we want to update the value of W1 and W0 through iterations, through consecutive process, and finally optimize so that we have a final value of W1 and W0 that will eventually lead to moving this predicted straight line to somewhere around this experimental data or the actual data, output data, where it kind of represent that, and the error then would be minimal as well. So for the consecutive updating process, or the improvement process, will have to run some sort of iteration, and we'll have to update W1 and W0 and basically optimize those in that process. So for that, let's run a while loop. So while iter is less than or equal max iter. So what is iter? Iter is basically just a random variable that we are defining to run this loop. And what is max iter? Max iter is the maximum number of iterations we want. We don't want it to be infinite. We want it to be like typical value that is normally used for this kind of issues, and this is like 1000 is very normal value to be considered. Like at least the initial value we can consider it as 1000. And so here we'll have to actually update our this linear straight line, the linear fit within this loop, not outside this loop. So let's move all of this here. Yeah. Now, right now, when it's under this loop, every time the loop runs, this straight line should update. But for that, we'll have to update W1 and W0 as well. So W0 say is equal to, so say that the updated W0 is equal to the old W0 plus dW0. So dW0 is the small change. Similarly, W1 is equal to W1 plus dW1, which is very small change in W. So every time that iteration goes, it works like that. Iteration increase by 1 at each step. Iteration is updated each step. Okay, so right now this is our new values of W0 and W naught and W1, but we'll have to define again what is W naught. W naught is kind of like the gradient that we should the equation of that we showed in the previous lecture. But there is also something called the learning rate that we are observing in this dw naught like with the gradient descent. So minus ALP, you can see the previous lecture to like compare the equation and understand this equation. So alpha sum of y divided by m and 1 equal to minus alpha sum of y, y into x over m. Yeah, so we have written the equations, but we don't know what is alpha, so we'll have to provide the value of alpha here. So this line we can remove. We just put it just to show the value, the initial case value, how it varies, but we actually don't need it for the plotting. So just to keep it lean, I'm removing that, and also I will put the value of alpha before I start the loop. So say this is 1.5. Yeah, so every time this loop runs, we have a new value of W naught and W1. It's gonna update every time. And when it updates, it's also gonna calculate a new cost function. As we know, the cost function is a function of these weights. So with the new weights, every time the cost function is gonna be updated. So J is equal to 0.5 over M multiplied by sum of y minus wx minus w naught. Again, how this equation comes, you can see from the previous lecture. It's not provided as a detail, but you can understand a little bit more like a guideline of where I'm coming from. But this one, every time this happens, with every iteration, it calculates a new cost function value. So so let's just go back a little bit and try to understand what I'm trying to do here. So with each iteration, so say with iteration 1, it starts a loop, and within this loop it first calculates the value of the first predicted linear function, or the straight line, how the straight line is going to be defined by that. And then it's trying to update the or improve the value of the weights, which is W1, which are W1 and W naught. And this is done through this process, through these four lines. And then it's gonna get, with this, it's gonna get a new W1 and W naught, which is different from the previous one. And then it's gonna calculate the new value of J. So J is the cost function. It's basically an array. We are defining it as an array that holds all the values of costs, or all the values of loss that are calculated in each of the iterations. So if there are maximum number of say if there are 1,000 iterations running, there will be 1,000 elements inside Z. So at max. So that's why we'll have to first define J is equal to np dot zeros max iter. So see from through this one I'm kind of initializing the list, the array of j. So, and like max iter, because this holds all the values of loss at all each of the iterations we are running. So maximum iteration number we'll have to put here, because it holds its length depends on how many iterations we are running. And then just see this thing. So we are calculating the cost, but we'll also have to calculate the error of the uh, error that the process is undergoing under each of the iteration, which we can find by this equation minus j. So here, as I described in the previous lecture, so the difference we need an error or a stopping criteria to stop the loop, because as the loop goes forward, it's gonna minimize the j, and it's gonna optimize the value of w1 and w0, and it's gonna be better and better, and at one point it's gonna get the optimal value, but the loop is gonna keep running. That's something that we don't want to do because of the cost and time, and therefore we want to put a stopping criteria. So this stopping criteria is provided by this error, which is the difference between these two values, the value of cost function for a certain iteration and the value of the cost function uh, in the previous iteration, and this difference should be minimized, and it should tend to zero, but it can never be zero, because if it's zero, it can never be basically zero, because the machine has its own precision, so it's gonna keep running. So we'll have to put a stopping criteria. Say we put a stopping criteria as to the power minus 5, and we'll have to also define the error, say is equal to 1. So we have this, and now if you see this equation, it calculates the error when it's for iteration 1. It goes inside this loop, comes to this point where uh, it has this value j iter. So iter value is 1, so basically it's j1 minus j1 iter is 1, so 1 minus 1, which is j0. So iter so j of 1 minus j of 0. So that's what it's calculating in the first iteration. But here we have the iteration value calculated, but not the value of the like first index, because any list actually the indexing starts from 0, not 1, but we have started the iteration from 1, so we are calculating this starting from 1. So we can calculate the value of j of 0 here before the loop starts, so that everything is in line. So this is gonna be basically the same equation. So the value of j0 and j1 will be calculated differently, because the value of w1 and w0 are different for these two cases, and therefore there will definitely be an error that is gonna drive the loop to continue to the next step, and that's how it's gonna keep continue. But in the process, the value of error is gonna be decreased, because the value of w1 and w0 is gonna be improved in a way that the error is decreased. So yeah, so that's how it should look like, and let's just, it should be like that. And yeah, so we have now the value of j. We also want to plot the value of j. So plt dot plot I'm gonna explain what is this, but before that, I'm just gonna write down the code. Okay. So here I have done few things. First, as we know that we want to draw two plots. So, and we, what I'm trying to do first, I'm trying to show the two relation, the y versus x relation that we have this plot here, and also another plot I want to draw, which is the value of the cost function versus the number of iterations. So these two I want to show together. So that's why I have splitted the single plot into two. And for that, I'll have to use this function, the subplot. So it's going to create two function. Okay, so here I have one error. It's not is equal to, it's actually, if it's greater than 0. So now if I run, yeah, so I can you can see that there are two different plots coming. On the top we have one plot and bottom another. Let's add some rendering here. plt.x level x plt.y level y, and this is gonna be iterations. This is gonna be cost function j. Okay, so if we plot this, yeah, you can see that we have the plot beta rendered here, and we know what's that, but we can see from the in the first plot we can see y and versus x, and in the second plot it's cost function versus the iteration. So we can see there are quite a number of problems or something going on there, but before that I just want to explain how this subplotting works. So see, in this subplotting we have this 211, this number, and this 212 number. What does it actually mean? So here there are basically three different terms. The first one represents row, second one represents column, and the third one represents index. So 2 means the row is splitted into like 2. So if this one is a single plot, there will be 2 row, and 1 is means that there will be one single column. The column value 1 means there is going to be one single column. So as we can see, there is just one single column. So if we wanted to put 4 pictures, like 4 plots together, there would have been 2. And then 1, the third number 1 is the index. So this plot, the y versus x, is gonna be the first one, and the second one, which is the cost function versus iterations, it's gonna be index 2. So the only difference is in the index number. We can also just swap it. We can also swap the value. Say if I put it 1 and if I put it 2, it's gonna be the other way around. But we can see like this is like the spacing between these two is not good. So let's fix it. So I will just put it back to the original state. So and try to fix the spacing between these two first. So for adjusting the spacing, I'll have to do another thing. I'll have to put another another function which is subplots underscore adjust h space equal to any value. So here this is a function which will vertically space out these two plots. Let's run it and we'll see. Yeah, we can see that right now we can see the x, so y versus x is well visible, and the cost function versus iteration is well visible as well. But how this through this function where we are using this h space is equal to 0.5. By adjusting this value, we can change the vertical spacing, and the h space, even though it's like means like horizontal space, it's actually vertically spacing out these two plots. Now, so quite a few number of things that we have to update. Number one is if you see y versus x, we'll have to add some legends, which are like what is this like this data mean, the x the predicted data as well as the experimental data. We want to put ligands for that, and that we can provide through this one. So the plot of this one is the, let's put label is equal to, it's, we're gonna call it data, or we can also call it experimental data. That's fine, whatever you want to call. And we can call it label is equal to, this is our prediction. So this is our linear feed, actually linear feed. But if we run it, you can see like we still cannot see this ligands. The reason of this is that it's not actually attached anywhere, and that's why when the program is running, it's getting lost somewhere. It's somewhere, but we cannot see this. So for that, we'll have to write another line here: plt dot gent underscore. So that's gonna be log equal to upper left. For example, we want it right here. So if we run it, okay. So what is actually happening here? It's quite an interesting thing. I can explain it. So after I have run it, it's going like this terrible situation where we have this all of this thing, and if you let's just this program just yeah. So if we just zoom it in, we can see like these ligands, these are all around. The reason of this is actually what is happening is one frame is on top of each other. So every time we're running this iteration, we're having one plot, and for the second iteration, we're having the like another plot on top of that, and for the third one, we have another plot adding, and that's how like one frame is adding on top of another. And that's why you can see there are two issues. Number one, these ligands are like all around, there's multiple ligands. And number two, you can see these straight lines, the linear feeds. There should be just one linear feed, but you can see like there are, I think, like a lot of linear feed. This is just rendering issue, and we can simply fix it by making sure that it doesn't overlap. Like each time it runs it, after each time this after each time the loop, the program runs through the loop, the plot is created, that should be deleted so that the next frame doesn't add over it, rather it comes as a fresh one. So that can be done through plt.clf. Yeah. So right now you can see like it's totally fine. It's those issues, the multiple regression line and multiple legions, those are removed because we have added this function. So what does this function actually do? So this is called clear. So this is clearing the function. So clearing the plot. So what is actually happening here? Say for the let's go from the very beginning. For iteration 1, it's going through this, and it's creating one plot. And for the next iteration, for the second iteration, when it's coming back, then for iteration 2 it's coming, and we still have that plot here, the first plot here for iteration 1. It's coming here until this point, and then when it this point is this statement is this sentence is executed, it deletes the old one, and then it starts over, and then and the next one, the next plot plot is being shown up as a fresh one, and that's why there is not like multiple frames overlapping. So what if we put this one this this sentence after this? Say we put it after this one. So it still works. It still works in this case. This is kind of a weird thing, but many of the cases it basically deletes it deletes this. And what how we can see that? So for example, say I'm gonna explain it a little bit later, but first see another thing. So I'm just gonna put it back. I'm gonna explain it later, but before that, let me explain another thing. So when I run it, so there are like not actually a single there is not actually a single iteration going on. There's a lot of iterations going on, and the plot, what we are seeing, is not stationary. It's actually a dynamic one. So when I run it, I cannot see any change in the plot, but it's not what it looks like. It's there are lots of things happening here, like all the many frames are changing here, but it's not visible because it's changing really fast. So we don't want that. We want to see the change in a gradual in a gradual manner. So for that, we'll have to do one thing. We'll have to add this function pause point one. Oh, sorry, so it's just typo. Yeah, now we can see like this is dynamically changing, and this kind of looks like this is what I was initially saying, that this is one of our objective, to see like how the relationships change dynamically. So this dynamic change is well visible when we add this function that shows the gradual change, because it's the time difference between each frame change is being like in the graphics, it's changing by 0.1. So we can actually update the time, we can increase it or decrease it to control how fast we want to make the change happen. But what if, so this thing that, as I was saying, so what if I put it here? So now you can see one interesting thing. So I'm running it, and I cannot see any change in the graph, because it's actually clearing up the graph when, like, in between the process, like in when the subplots are done, at the end it's clearing the plot. But we don't want that. We want that to be cleared before the subplots are drawn. So we can count each of the iterations. So we can visualize each of the iterations. Now, as you can see, we can see each of the iterations, and sometimes we can see like this is not well visible for some reason. Then we just have to add this one. Luckily, this is not showing in an error. But if this doesn't show this dynamic change, or the plots are not showing up properly, just add this function as well. So yeah, so this is one, and let's just we can also change the color of this one. So I want green for the cost function, so I'm just changing it to green. But here a few things. First, like if we go through this code again, so I think all of this is well understandable, except like I have already explained everything except this line. So how this line is coded, or what actually is intended, or what is actually being done through this one. So here what we intend to do is to plot the cost function versus the iteration, which is the bottom curve here, the bottom plot here. So along the x-axis, we want to put all the values of the iterations, which is provided by this function np.arrange, and along the y-axis, this is the element of the cost function j. So how does it work? So along the x-axis, through this function, see this one. So for iteration 1, when it comes, we have iter plus 1, 1 plus 1, so it's gonna be 2. So 1 to 2. So np arrange 1 to 2 for iteration 1. What does it actually mean? It basically means that it's gonna take value from 1 to to the next value, which is less than 2. This is basically 1. So again, let's just write this one. So np dot arrange 1 to iter is 1. So this is the first value, this is the second value. So this function, when it has these two value, it means how many value is actually storing. So it's actually storing values starting from 1 to the values that is less than this final value, 1 less than this final value. So say if iteration was 1000, say iter was 1000, then this would store a value of 1 to 999. So right now it has 1 iter plus 1. So it's actually taking value from 1 to iter. So it's taking all the values of iterations, because the iteration starts from 1, iter is equal to 1 to iter is equal to iter. So throughout the loop, that's what is happening here. So it's taking all the value of iteration. That's what I try to mean through this portion. And here, but remember, this is getting changed every time we are doing, because the size of this is changing as the value of iter is changing. This is variable, right? So if it's increasing, the size of this is increasing as well. The next one is also changing. So iter, the value, as the value of iter is changing, j is also changing. So say for iteration is equal to 1, what happened when iter is equal to 1? It comes here and we have 1 to 1 plus 1, which is 2. So 1 comma 2, which is basically it's storing the value of only 1, because it cannot store 2. The final value, if the final value is 2, it's gonna take the value, take the final value as less than what is provided here, 1 less than what is provided here. So it can only store 1. So it's gonna start from iteration is equal to 1. So as iteration 1, it's gonna the first iteration is gonna bring us right in the right here after in the plot. If you can see in the bottom plot, right after 0 at 1, it's gonna shoot in this position, and for that it's gonna plot the corresponding value of j. The corresponding value of the of the value j is what? The corresponding value of j is j of 1 minus, so this thing is let us calculate the corresponding value here. So for iteration 1, np dot arrange 1 to 2, which basically mean 1, the iterations equal to 1, and the corresponding y value for iteration 1, x value for iteration 1, and corresponding y value is j of, here iter is equal to 1, so the value of this would be j of 1. So it means it's gonna take value of j starting from index 0 to index 1. So again, so it's not gonna, similar to this one, it's not gonna take the final value, it's not gonna take 1, it's gonna take value less than 1. So it's gonna take the value 1 less than the final value, which is 1. So 1 minus 1 is 0, so it's only gonna take j of 0. Yeah. So for the first iteration, it's gonna be iteration is equal to 1, and the corresponding value of this y value would be j is equal to 0, which we calculated at the very beginning. So it's gonna be right on the top. And then when we calculate the second one, let's just copy this. So for iteration 2, what is happening? This is gonna be 1 plus iter for this time is 2, so it's gonna be 2 plus 1 is equal to 3. So it's gonna take 1 and the final value is 3, so 1 less than final value, so it's gonna be 2. So 1 to 2, so the iteration value would be 2. So it's gonna be 1 2, so the iteration value is gonna be 2, and the y value accordingly the y value is gonna be, because now it's 2, it's gonna take from 0 to 2, which is 0 and 1. So for the next iteration, it's gonna take index j is equal to 0 and j is equal to 1. So for the next iteration, we can see it's gonna take the first two value, right? So just think about this, like every time we are so that it doesn't confuse you, every time we are running the plot, we are actually getting a new fresh plot. So for the first plot, what is actually happening, we are only getting, for 1 we are getting this data, and for iteration 2 we are getting for for 1 and 2, iteration number 1 and 2, and we are getting these two data. Similarly, for 3 iteration, this is we are gonna get this 3 data, and for the 4th iteration we are gonna get 4 data, and like this for n iteration we are gonna get n data of n value of j. So that's how it's working. I don't know if it was much complicated, but I would let you brainstorm and understand it. Please let me know if this doesn't seem to be much clear. I can explain it further. Yeah, so that is how we code this plot for linear regression algorithm. And yeah, so as we have we run this code, we have this final linear fit, which is represented by this equation again, which is y hat is equal to w1 into x plus w naught, where w1 and w1 and w naught are the parameters that we have optimized through this loop. And so right now, whatever value we are getting for w1 and w naught is the optimized value, and this is what was the whole purpose of doing all of this. And how these values of w1 w naught came to this optimal value, or this best fits, representing this best fit is associated with how we are changing the cost function along with it. So the cost function, as the w value is improving, the value of the cost function is decreasing, and at one point it's going to 0, and it's not going to exactly 0, it's going to be like close to 0. And that's why, because it's important so that the loop doesn't run infinitely, and that's why we have put the error, which is the stopping criteria. We can choose this value. If this doesn't work fine, sometimes it doesn't work fine, then we'll have to play around with the parameters, our initial guesses. Most important such parameter is the learning rate alpha. But also see here, like if we can also find out the value of w naught, which is this, and w1, which is this. So we can put this final values of w naught and w1 into this equation, the predicted value, and thus we can predict any values that are not directly provided as a data point. And yeah, so also we can see the how the value of the cost function changes. So, and how much is done, how many iterations it took, even though we wanted we initially provided max iteration is equal to 1000. Let's see how much iterations it actually took. So from the plot here we can see the iteration it took is like slightly over 70. So it didn't even take 1000 iterations. So it would so if we didn't provide this error, it would actually run all the 1000 iterations, and that would take more time, more cost. And how many iteration it took? Iter is equal to 70. So it basically took 72 iterations only, so less than 10% of what we initially thought would be good for it. And also the value of j, we can see that it's decreasing, which we initially said that it should be decreasing, which also marks that we are going in the right path. But how it's changing, we can see that as the least. So from here we can see this is the array printed, the final array printed. So initially we had said this is so this is a quite a big array, because we defined it as max iter to be to be an array, the parameter we have set as max iter, which is 1000. That's why it's so big. But see, the value, the initial value of this was like quite big, and then gradually it started uh, decreasing from 8, it decreased like significantly. And we can see by certain, like it went to the zeroth order, like after quite after running for a while. And that's how we can see all of this, what's happening in this plot, in numerical values as well, by just putting these parameters here. But some more interesting things to, like, if we see like what would happen if we just make it say 2. So we are just changing this line space. So we can see, like, for when we put when we change the x value, this is behaving really odd. This is really behaving weirdly, and it's kind of oscillating. It doesn't seem to be like converging like it was converging for the previous case. It doesn't seem to be converging. So why it's actually happening? So what we actually have done, we have changed the space. So the same data, so the data is the number of data is 51, but it's instead of 0 to 1, we have it from 0 to 2. So that's why the space along the x-axis is increased, so increased by twice. So but this increase, why it's causing this to happen, to be behaving in a very different way than the previous case. So the reason for this, let's just explain it a little bit. So from 0 to 1, when the range was from 0 to 1, the data point, all of the data point, the along the y-axis, when we plot it, so these data points, marked by the cross, were calculated based on these values, and these were like closer together. But when this is we are just increasing the spacing between the data of the x values. So what is actually happening here, say the value, the difference between the two x value is increasing. If the value between the two x value increases, it's gonna eventually increase the value of y, because y is a function of x. So therefore it's gonna be increased significantly. So what is y? Y is the actual value, but we are predicting with the same initial assumption. That's the problem, because right now the y value is far off than like it was definitely off previously, but it's right now like way more off, because the y value, it's much change depending on the value of x. For this case, we can actually change the initial the value of the predicted uh, the guess for the parameters, which are w0 and w1. We can just change it. So we can multiply it by some value, or probably we can, if we don't want to randomly put, we can put some values bigger, or like play around with that. But the best way to work with that is to work with the learning rate. So we can actually update the learning rate to make it better. So for example, like ideally we would want to go lower. So 1.5 is something that we started with, but if it didn't work, if it worked, if for the previous case it worked like this weirdly, we would definitely go lower learning rate. But luckily it worked for us, so we didn't go lower. But say it didn't work, like it doesn't work this way, we go to 1, and then we run again, it's still behaving this weirdly. So we stop and say we make it 0.1, 0.1. And now you can see right now it's converging again, like with this value it's converging. So here like this is very important, that even if it doesn't run, we have to play around with the alpha, and finally it will work, and eventually we're gonna get the values of desired optimal parameters. Yeah, thank you very much. If you have any questions, please feel free to reach out. And yeah, these plots we can always these plots in our projects, and also like we can make videos, and like we for the dynamic changes to show how the changes are happening. Thank you very much.